Okay, so this is the beginning of Unit 3 on covalent bonding and intermolecular forces. This is part of IB Topic 4, but not all of IB Topic 4. So previously we've looked at elements and compounds, atoms and molecules, solutions. In Topic 1 we took like a quantitative approach and talked about moles and mass and how we measure those different things. And then in Unit 2 we looked at atomic structure, so we went in depth inside the atom to understand the properties of individual atoms, and then those properties we looked at how they changed gradually across the periodic table. So that was all in Unit 2. Now we're going to take those properties that we talked about on the periodic table, things like atomic radius and electronegativity, and we're going to see how those influence how atoms interact with each other, and specifically how they bond together. Because as interesting as the elements are and how they change and their properties, chemistry gets much more interesting when elements begin to bond together to form compounds, because there's 118 elements, but there are millions and millions of different compounds, and you and I are mostly composed of compounds, not pure elements. So chemistry gets much more interesting once we can talk about bonding. So it's really key just to recap and remind ourselves about one of the most important properties from last unit for this upcoming unit, Unit 3. And that is, Z effective, the effective nuclear charge, but also electronegativity. So the trend for Z effective across the table was it increased with fewer principal energy levels, and it also increased if we had the same principal energy levels and the same shielding effect. It would increase across the table left to right as we increase the number of protons. So we get more Z effective with less principal energy levels and less shielding effect, and we get an increase in Z effective as we get the same principal energy levels but more protons. So hopefully that's all relatively familiar from last topic. So these are the directions of increasing attraction for electrons, and we could kind of combine them to say that the general increase in Z effective is in that direction. All right, let me stick the charger in here. One moment. Cool. All right. Now, what is the trend for electronegativity? The electronegativity trend is just like the Z effective trend. So electronegativity is the ability of an atom to attract an electron pair when bonding. This topic is about bonding, so now electronegativity becomes really important. The one thing to remember about electronegativity is that the noble gases, with a couple of weird exceptions, they don't really get electronegativities because they don't typically bond. So the only way that electronegativity can be measured is when atoms are bonding with each other. You look at how the electron pair gets attracted towards one element, one atom versus another. So since they typically don't bond, they typically don't have electronegativity values at all. So that means with this trend, the highest electronegativity we should predict would be fluorine. It's the element at the upper right corner of the table that's not a noble gas, that doesn't have a full valence shell. So that happens to be the case. Fluorine is the highest electronegativity with 4.0, and oxygen and chlorine are the second highest electronegativities. Here, oxygen second with 3.4 and chlorine third with 3.2. So that upper right-hand corner, high Z effective, high electronegativity. And that's a property that we associate with nonmetals. So if I zigzag across this table like this, the nonmetals are these elements over here, the noble gases included and hydrogen included. So those are our non-metals. So they're going to be the main focus of our unit here, because covalent bonding is the type of bonding that we associate typically with nonmetals. Now there are other elements, metalloids and some metals, that can also covalent bond, but it's most closely associated with nonmetals. And nonmetals are elements that have high electronegativity in general, not the noble gases of course, but that have high attraction for electrons. And that's what makes nonmetals insulators, electrical insulators. Because they attract electrons strongly, that means electrons can't move freely across them with few exceptions, and therefore they typically don't conduct electricity. All the elements in the middle we've talked about here, these ones along the staircase, I can pick these, let's see, not aluminum, sorry. Forget I highlighted that. Let's erase that so I don't mess you up. These ones here are the ones that are considered to be the metalloids, the ones I've circled in red. There was my Z effective trend that I just got rid of. That was going this way. Cool. And so that means that all of these elements over here, these are our metals. And metals we associate with having a loose hold on electrons, a loose attraction, low attraction for electrons. We'll come back to metals later in other topics. But for now, remembering our Z effective trend and our electronegativity trend, and that nonmetals have high attraction for electrons is relevant for understanding about bonding. So there are three types of intramolecular chemical bonding. In future units, we're going to talk about the other two, which are ionic bonding and metallic bonding. But for this unit, we're just going to focus in on this middle type, covalent bonding. So covalent bonding happens for nonmetal elements when they bond with other nonmetal elements. Now that's a generalization. Like I said, it can also happen. It can happen with metalloids, and it can happen with metals as well. But typically we associate it with elements that have high electronegativity. When different elements, different atoms get together that both have high electronegativity, they end up, both of the atoms are going to attract the valence electrons relatively strongly. And that will mean that neither one of those atoms can steal the electrons from the other atom. And so what ends up happening is that the valence electrons are shared in pairs. So in covalent bonding, you can remember that carrying is sharing, or share, sorry, I said that wrong. Oh, geez, said it all backwards. So you say sharing is caring, because that's an expression people know. Sharing is caring, and caring is covalent. And you'll remember that, okay? So covalent bonding, like they're together, they're sharing electron pairs. And this picture up here is meant to show you, don't get too bogged down in some of the confusing parts of it, but you can see these sort of orbitals sticking out from each atom, and they're overlapping, and there are these two dots that are kind of in the Venn diagram center portion where they overlap. And those are the shared electron pairs. So these two dots being drawn together, that's how we're going to be drawing representing electrons in our structures that we draw this unit. And so in covalent bonding, we're talking about sharing electron pairs. And so the actual bond, the actual thing that holds the two atoms together, is referred to as an electrostatic attraction. Electrostatic just means it's about positive and negative electrical charges. So it's an electrostatic attraction between the two positive nuclei. That's the positive part. There's a nucleus in this atom that's positive, and there's a nucleus in this central atom here that's positive. I'll switch my color. So every atom has a nucleus that's positive. We know that from like our Z effective talk and all the different properties that we looked at. And there are shared electrons between them, and both nuclei, positively charged nuclei, are trying to pull on those electrons, and so that keeps the two atoms together. So one key definition, it's right on the syllabus, that you need to be able to write out yourself, is that a covalent bond is the electrostatic attraction between the two positive nuclei and the shared electron pairs between them. Okay, so covalent bonding is between atoms that have high electronegativity. This results in strong attraction from both atoms for the electron pairs, so they end up sharing the electron pairs. And if we have to describe the attraction, we would define it this way, what I just started up there. And there are lots and lots of examples of molecules. There's so many different kinds of molecules. All of organic chemistry is based on covalent bonding. We've seen examples already of elements like H2 and O2, those diatomic elements. Those atoms were held together by covalent bonds. Water held together by covalent bonds, carbon dioxide, glucose. The possibilities are pretty much endless. Okay, so the next concept to talk about in the covalent bonds is that not all covalent bonds are exactly the same. Covalent bonds have something or they can have something that's referred to as polarity. And polarity is a way of describing how unevenly the electron pairs are shared in a covalent bond. So we say that the electron pairs are shared between the two atoms, but they're not necessarily shared evenly. And the way to determine how evenly they are shared is with that property of electronegativity again, specifically looking at how different the electronegativity values are for two atoms. So if two atoms that are bonding have almost the exact same electronegativity, or in fact they do have the exact same electronegativity, then they end up sharing the electron pair completely evenly, 100% covalent sharing. And that's what's called a nonpolar covalent bond, where the electron pairs are shared more or less evenly. So the classic examples of really nonpolar bonding are all of those diatomic elements that we talked about, because F has an electronegativity of 4, which is very high, but if it's bonded to itself, then they both have an attraction of 4, and so the electron pair will spend most of its time right between the two atoms, and the electrons will spread out evenly around that bond. So the electronegativity difference is 0. And that means that the bond is perfectly nonpolar. Now, on the other hand, if you have two elements where the electronegativity difference is larger, like hydrogen and chlorine in this example, hydrogen has an electronegativity value of 2.2 and chlorine 3.2. And remember, these values are all listed in a data table in the data booklet. So in this case, the difference between them is 1. So that value is significant enough that it puts that bond into a category that's called a polar covalent bond. So the electron pairs are still being shared, they're still in between the two nuclei, but because chlorine has a much stronger attraction for them, they spend more of their time on this end of the molecule, this end of the bond, than they do on this end of the molecule, or that bond. And what that results in is a little tiny bit of charge, of negative charge at the end where we have the chlorine atom, and a little bit of positive charge on the end where we have the hydrogen atom. So it doesn't mean that it's an ionic bond. We haven't formed full charges, but there is this very tiny amount of charge on either end of that hydrogen to chlorine bond. So those are called partial charges. You'll notice I used this funny symbol here. It's actually a lowercase Greek delta. It kind of looks like a squiggly lowercase d. And so that's to imply that the chlorine end of this molecule, or this bond, is a little bit negative because the electrons are kind of more heavily on this end of the molecule. There's more electron density there. And there's not much electron density near the hydrogen, so that end ends up being a little bit positive. So that's one way to try to represent this polarity. The other way to do that is with something called a dipole arrow. And a dipole arrow is like an arrow with a little positive charge for a tail, and you draw the arrow pointing towards the higher electronegativity. So it shows you where the electron pair would be more attracted. And so since chlorine has a higher electronegativity, we would draw the arrow towards the chlorine, and that would tell us where the electron pair is being attracted and which end is a little bit positive near the hydrogen. So understanding that when two atoms come together, depending on how their electronegativity values compare, that will determine exactly what kind of bond they form. So they can form a nonpolar covalent bond where electrons are shared relatively evenly. They can form a polar bond, and with increasing difference in electronegativity, you get increasing polarity. So it's a continuum. So the bigger and bigger the difference in electronegativity, the more and more polarized it gets, the more and more negative and positive those ends get. And the ranges are that from 0 to 0.4 difference, you have what you call a nonpolar covalent bond. Even though a 0.4 difference would be a very slight polarity, we would refer to it as a nonpolar bond. If the difference is 0.5 up to 1.8, then we call that a polar covalent bond. And then if it's greater, if the difference is greater than 1.8, then we pass over into the next type of bonding that we call ionic, where the difference is so great that actually one of the elements fully steals electrons away from the other. So they're no longer sharing, and electrons get transferred from one atom to another. So we're not really going to deal with those ionic bonds here, but we are going to look at these electronegativity differences to try to assess if bonds are polar or nonpolar. Now, metallic bonding, again, another future topic. It's left off this chart because all metals have very low electronegativities. So even though there's a small electronegativity difference, their electronegativities are so low that they don't actually attract the electrons strongly enough to form covalent bonds. So just in case you were wondering, like, hey, where's the metallic bonding on this chart? It's left off for a reason. You don't have to worry about metals and other metals forming covalent bonds together typically. Okay, last thing for this video is that typically when elements are covalent bonding, they do so in such a way that they end up with a full outer shell, usually an octet of valence electrons. And they get that through a combination of shared electrons, shared electron pairs, and unshared valence electron pairs. So the ones that they share with one another are called the bonding pairs of electrons, and the ones that they keep to themselves are called the non-bonding pairs of electrons. And so what we end up with is, by sharing electrons together, then each atom feels like it owns those electrons to an extent, and it can end up with like a noble gas electron configuration, which we've seen before is a very stable configuration. So pretty much everything ends up covalently bonding to achieve the feeling of that full outer shell noble gas configuration. Bonding pairs, like I said, count towards the total number of electrons for each atom, the total number of valence electrons. And when things are bonding, they can form single bonds, which is one pair of electrons or two electrons. Two atoms can double bond with each other, which means they can share two electron pairs together. Or atoms can triple bond, and then that will be 3 electron pairs or 6 electrons shared between the two atoms. Non-bonding pairs only belong to the atom that they are on. So these drawings here, these structures are called Lewis structures. And you're going to do some practice with them, or lots of practice with them during this unit. They're not perfect, but they are one way to try to represent how elements are bonding with one another. So in these structures, typically, what we'll see is that bonds most often get represented by lines, little line segments. So that represents an electron pair, that's a bonding pair. And that's a bonding pair. And then the lone pairs typically get drawn as pairs of dots. So here, these are called non-bonding pairs, or you already heard me say it, I often will just call them lone pairs, and that's also a way to refer to them. So in this one, we have 2 lone pairs around oxygen, and it also has 2 bonding pairs. And so if you realize that a pair contains 2, so the 2 lone pairs is 4 electrons, and the 2 bonding pairs is 4 electrons. And so in total, oxygen ends up feeling like it has 8 electrons, which is a full outer shell. So that's stabilizing for oxygen. To form these 2 bonds with hydrogen, in the end, oxygen now feels like it has an octet. What about hydrogen? Well, hydrogen just has this one bonding pair each, right? Each hydrogen just has 1 pair. Well, 1 pair is 2 electrons, and hydrogen is so small, it only has that first energy level. 2 electrons is a full valence shell for hydrogen. It has the configuration of helium. So by doing the bonding this way, a single bond for each hydrogen and 2 bonds for oxygen, each atom is able to feel like it has a full outer shell by sharing these electron pairs together. And you'd see the same thing in these ones. Each hydrogen always, if it covalently bonds, only forms 1 bond, and then it gets to feel like it has 2 electrons, each hydrogen. And nitrogen begins with 5 of its own valence electrons, right? It has these, if we think of its 5, but because it's now bonded with hydrogen, it gets to feel like it has 3 more. So for each bond, it now has shared 3 additional electrons. So each nitrogen feels like it has 8 electrons as a result of these 3 bonds. And a final example that involves something more than a single bond is a double bond. Carbon typically has 4 valence electrons. So in this Lewis dot structure system, we would think of it with 4 dots, 4 valence electrons. Each oxygen on its own has 6 valence electrons. And we would use a periodic table to help remind us of this. So oxygen, because it has 6, it needs 2 more. So it typically forms 2 bonds to get those 2 more electrons around itself. If it shares 2 more, it can have 8 around itself. Now there's 2 oxygens here, and each of them needs to form 2 bonds in order to get a full outer shell. Carbon has 4 valence electrons, so it typically forms 4 bonds to get a full outer shell. And so all the atoms can end up being satisfied if carbon forms a double bond to each oxygen. So now this oxygen feels like it has 8. This oxygen feels like it is 8. And the carbon in the middle feels like it's got 4 here and it's got 4 there. It also feels like it is 8. So all of them now feel like they have that full octet of electrons. So the combination of bonding electrons and non-bonding electron pairs has to add up to a full outer shell in nearly any example that we're going to look at. Okay? I'll do a little bit more after this, but that's your introduction to the theory of covalent bonding, how covalent bonds can be polar or non-polar depending on the exact electronegativity difference, and the fact that things are going to covalently bond in a way and form molecules in such a way that they end up with a full outer shell of valence electrons between their bonding pairs and their non-bonding pairs.